Have you ever really stopped to think about what makes a battery work? Or why some chemical reactions just happen, all on their own, while others need a serious push? Well, it turns out there's this fundamental driving force behind it all, almost like a secret language that decides if a reaction is going to go. And today, we're going to decode it. Right, let's get straight to it. What is this chemical push or pull that makes a reaction spontaneous? What's actually convincing electrons to get up and move, powering everything from your phone to your car? That's the big mystery we're diving into. So, to figure this all out, we need to look at a reaction's dashboard, so to speak. There are three key gauges that chemists use to see if a reaction is going to happen on its own, under those ideal, squeaky clean lab conditions. Okay, our first gauge is the standard cell potential. The easiest way to think about this is as the reaction's voltage. It's the electrical push. And the rule here is super simple. If that voltage is positive, the reaction is spontaneous. The electrons are good to go. Next up, we have the standard free energy change, or what we call delta G. This tells us how much energy is actually free to do something useful, like work. But here's the twist. For this one, you're looking for a negative number. A negative value means the reaction is giving off energy, so it's ready to roll. And finally, we've got the equilibrium constant K. Now this one isn't about the initial push, it's about the final destination. It tells you the ratio of products to reactants once everything is settled down. And if K is a big number, bigger than 1, it means the reaction heavily favors making products. So we have voltage, we have energy, and we have the final product score. At first glance, these seem like three totally different measurements. But, and this is the really beautiful part, they aren't different at all. They're all connected by a couple of elegant equations, almost like a chemical Rosetta Stone. That's the key takeaway right here. These three values, E naught, delta G naught, and K, are really just three different ways of telling the exact same story. If one of them tells you a reaction is spontaneous, you can bet the other two are going to say the exact same thing. Every single time. They're all tied together. And here's our first connection. This equation shows that free energy and cell potential are basically two sides of the same coin. See that little negative sign? That's the whole magic trick. It's a mathematical guarantee that when the voltage is positive, the free energy has to be negative. They're both screaming the same thing. This reaction is spontaneous. But it doesn't stop there. This next equation ties the cell's voltage directly to that equilibrium constant K. All the letters can look a little intimidating, but the core idea is simple. A really strong electrical push, a big positive voltage, means the reaction is going to end up with a ton of products, which gives you a massive value for K. So let's put it all together in a little cheat sheet. For any spontaneous reaction, the pattern is always the same. Negative free energy, positive voltage, and a K value greater than 1. If a reaction is not spontaneous, everything just flips. And if it's perfectly balanced at equilibrium, everything just lands on 0. It's this perfectly elegant and consistent system. All right, enough theory. Let's actually put this to the test. We're going to take a real-world reaction between silver ions and some solid iron, and we'll run it through our process. First, we'll calculate the voltage. Then, we'll use that to find the free energy. And finally, we'll solve for that all-important equilibrium constant K. So after you crunch all the numbers using those equations, this is what you get for K. And no, that is not a typo. That is 1.3 with 42 zeros after it. I mean, to call this number large doesn't even begin to cover it. It's just astronomically huge. And this is exactly what our source material concludes. A K value this big means the reaction doesn't just lean towards the products, it absolutely stampedes towards them. It basically goes to completion. For every one single set of reactants you might find at the end, there are 10 to the 42nd power sets of products. It's a one-way street for all practical purposes. Now, everything we've talked about so far has been under what we call standard conditions. Think of it as a perfect, idealized world you'd only find in a textbook. But what about the real world, where things are never that neat and tidy? Yeah, see, standard conditions are super rigid. Everything is set to 1 molar concentration, 1 atmosphere of pressure, 25 degrees Celsius. But in the real world, in your car battery on a cold day, or inside a living cell, all of those things are constantly changing. So our perfect model is a great starting point, but it's definitely not the whole story. To handle all that messiness of reality, our standard equations just aren't quite enough. We need something more powerful, something more flexible that can actually account for these non-standard, real-world conditions. We need a new equation. And this is it. The Nernst equation. This is the absolute key. It starts with our old friend, the standard potential, E naught, but then it adjusts it. It adds a correction factor, and that correction is based on the temperature and, most importantly, on Q. Think of Q as just a snapshot of the reaction's product-to-reactant ratio at any given moment, not just at the very end. Now, the Nernst equation opens the door to some really fascinating and, frankly, kind of mind-bending stuff. So let's look at one of the coolest examples. A device set on paper looks like it should be completely useless. It's called a concentration cell. The setup here is just wild because of how simple it is. Picture this. You have two beakers. Each one has a zinc electrode sitting in a solution of zinc ions. Everything is identical. The metal, the solution, everything. The only difference is that the concentration of the zinc solution in one beaker is way higher than in the other. That's it. So, if you try to calculate the standard cell potential for this thing, what do you get? Well, since both sides are identical, their potentials cancel each other out perfectly. The standard potential, E naught, is 0, a big fat 0. Looks like a total dud, right? So that's the big puzzle. We have a cell that our standard rules say has 0 potential. It should be at equilibrium, totally dead in the water. So how on earth does it generate any power at all? The Nernst equation is the hero here. The moment we plug those different concentrations into that Q part of the equation, everything changes. The equation is no longer 0. That difference in concentration, that simple imbalance, is enough to create an electrical potential. Nature wants to even things out, and that drive is enough to push electrons and create a real, measurable voltage. So let's just recap the journey we took here. We started with 3 totally different ways to measure a reaction's driving force: its voltage, its free energy, and where it ends up at equilibrium. We saw how they're all just speaking different languages to tell the exact same story. Then we left the perfect lab behind, jumped into the messy real world, and used the Nernst equation to find something amazing: that even a tiny imbalance, like a difference in concentration, is enough for nature to generate power. And that really leaves us with a final, pretty cool thought. We've just seen that the universe is always trying to balance itself out, and that we can harness that drive for energy. So if something as simple as a difference in concentration has this much potential, it really makes you wonder, doesn't it? What other hidden potentials, what other subtle imbalances are out there all around us, just waiting for us to figure out how to unlock them?